Okay, so where we last left off
assuming
was
our objective
going through the vectorization notation and
is
writing
to
the
pull
Mueller
out the
tensor in
elements of
vectorized
the Mueller
form.
tensor.
And we resulted in an expression
From
that had this
measurements
sort
of
of
the Stokes
annoying
vector for
ascending,
double frequency or some
ascending
other
product
intensity
of Jones
dependent
tensor elements,
variable.
which was not something we'd
As a
seen
function
previously.
of the input
We'd likely
polarizations.
turn it into that
Then we
product
run
of
into a bit
Jones
of a
tensor
problem
elements,
using the
which
tensor
is the
notation
exact
because
same
it's
terms in
going to
each
be
product, but
difficult
just
to
in a different
mathematically
order.
invert and using
And
linear
the question is,
algebra
how do we
in order to
connect them back?
isolate
And the
the
advantage of
elements
putting it
from the
into
Mueller
this
tensor
architecture is if
themselves.
it's in here, then we now have at
So,
our disposal
because
all of
this
the tools that
little
we built
snippet
up
is
describing
vectorization of the Mueller
the
tensor.
Jones
So we'll turn
tensor
this
framework.
into something
In which
can be
this,
pulled out,
which
in
includes
vectorized
this
form,
this
and then
Kronecker product
solve for it
ubiquitously
using linear
throughout.
algebra.
So if we can get the Mueller tensor
I'll
written
start before
in
going
terms
into
of this
vectorization of
rightmost
tensors.
vectorized Kronecker
Briefly
product of
review
Jones tensor
vectorization
elements, and
of
life is
matrices,
easy.
because that'll serve as the
And the way that we
foundation.
do that is we have to
So,
rearrange the tensor
for
elements
vectorization of the
in
matrix,
this term to make them look like the
vec
tensor elements in
operator
that
is
term.
well
And we do this
established, and this is
with the
order
matrix
of
E, which will
elements
allow us
that
to resort.
emerged in the vectorization,
That's the objective of
in
this
vectors,
discussion,
in
figuring out how to
vectorization of
populate
matrices,
that elementary matrix E.
It's not
So
difficult.
before
There's no,
going into
controversy
the
over
actual elements of E
ordering
themselves,
of
I think it
elements
makes
at
sense
all.
to just take a
Turns
step back
out
and
when you
remind
get to
ourselves
tensors, does
how
start
and
to
why
be a
the
bit,
ordering of the elements
interesting
appears
in
inside
terms of the fact that
each
you
of
don't
these
necessarily
tensor
know
element
which particular
combinations.
elements should go in
And for the
order unless
for
there's
the
some
one on the right here,
pre-established
the ascending product as
so we're going to build that
pre-established.
pre-established.
This is in the ascending product form.
vectorization format, and that's indicated
You
by
might
the
ask,
arrow
I think it's
over
easiest
the
rather than going
tensor.
through and trying to figure out where each one
So the
is.
ascending
that
vector
let's
format,
just look
the
at
tensor
one and
elements
see where it goes. We're
always
going to consider,
increase
for example, the HHV
in,
star
in binary
HVV
form.
combination. So where does this particular one of the 64? Where does this one particular tensor element combination sit in both this combination and that combination, and why are they different? Because if we can sort that out, then we can figure out how to rearrange them using the matrix E. So the way that we populate it is actually easiest to show on this. So if we've got the HHV HVV combination, then for this binary ordering, the first two indices, this one, H and H, correspond to the polarization state for the double light. The next two correspond to the polarization state for the first of the two incident fields, driving fields, and then the last two correspond to the polarization states of the lastmost driving fields. So if this was some frequency generation, this one and this one would contribute to the sum frequency. This one and this one would contribute to omega A, and this one and this one would contribute to omega B. And so the total would be, if I was to write this down, I'll try and color code them now, I'd have a 0, 0 corresponding to the red here. And in this particular ordering, for the ordering over here, it'll be 0, 0. So these will be the two red ones, because we're taking the first three Jones tensor elements and then the next three indices and multiplying those together. So that you can see now the difference in the orderings. If I consider now the blue one corresponding to H and V, then the blue will go here, and blue will go here, and here. And then finally the green, corresponding to V and V, will go there, and will go there, and there. So they're in different places in each of the two arrangements. But the color helps a bit in terms of disentangling where each one should go. So we now know where to put these, and we can take advantage of the fact that those zeros and ones are more than just convenient placekeepers. They actually tell us the decimal position if we convert them to decimal from binary. So for example, the 1011 position, which would correspond to HHV, HVV in this ordering, is in the 11th position in this particular tensor product. The corresponding element in the ascending vectorization of the product is in the 7th position, also given by binary counting. So now we have an easy way to connect what initially appears in here that we want to resort and put into there. And so in this case, we know that E11.7 was equal to 1, which would convert from the HHV, HVV ordering in this notation over into the desired notation. Actually, I take it back. This would be E inverse, because as it's used in this equation, we're converting this combination into ascending vectorized, into the ascending form of the Kronecker product. So in fact, E would do the opposite. It would take what starts out in this form and turn it into that form. So that would actually be E711 equals 1. And we'll just forget I wrote that. I didn't write that. You didn't see me write that. All right. So that's how we're going to be doing the remapping throughout all of it. We'll just basically do it one element at a time. It's actually not hard to just put this into a programming loop and have it write up what each individual element of E should be. It's going to consist of 64 ones and a whole lot of zeros in the 64 by 64 element matrix. And it'll just resort the different tensor elements. So it's a sparse matrix. In fact, if you're doing this in programming, I wouldn't even bother writing it with a matrix form. I would simply just resort the tensor elements manually and go from there.